So linear regression. So let's solve this linear regression problem by using neural networks. So what is linear regression problem? So let's say we are given this data set of xi's and yi's. So this xi's are the features and this yi is the class label in case of classification. These xi's are features, or it's a data point features, data point. So for this xi, this yi is the class label in case of classification. So for example, this yi can be a positive class or a negative class, right? Or it can be a zero class or it can be a class 1, right? So for binary classification problem, this yi can be either 0 or 1 or positive or negative. In case of regression, this yi is a real number, real number. Right? For example, if let's say we are given a data set of houses and their prices, right? So let's say the features of these houses we are considering are features. We are considering are, let's say first feature is number of bedrooms, number of bedrooms in the house. Second feature is, let's say, number of bathrooms. And let's say third feature is, let's say, number of car parkings. So these three features we are considering. So let's say now for first house. So the number of bedrooms are, let's say, three. Number of car parkings are, let's say, number of bathrooms are, let's say, I'm sorry, number of bathrooms are two, and number of car parks are, let's say, two, right? So this is x1, x1, right? And for this house, let's say the price is, let's say, 500.5k dollars, right? So it's a dollar 500.5k. Okay, so this is x1 and this is y1. Similarly, for second house, which is the features which we are calling at x2, is, let's say, there are four bedrooms and there are three bathrooms and there are three car parks. So let's say the price for this house is, let's say, 700 k dollars, right? So this is x2 and this is y2. Now the point to note here is this y2 or these yi's are real numbers. Right? So given the houses and their prices, right? So the problem here can be, let's say now for a unknown house, I mean for a new house, we are given these features and we are asked to predict this price of the house. So this price of the house can be a real number, right? So that's what our data set is. We are given xi's and yi's. So these xi's are nothing but this, right? So here xi for x1, this was x1, x11, x12, x13. x11 was 3, x12 was 2, 2. This is feature 1, feature 2, and feature 3. And this y1 was 500.5k dollars, right? So that is our data set. So the point to note is these yi's are real numbers. In classification, these yi's are not real numbers. They are some class like whether positive, negative, or a number, integer sort of number, right? Okay, so now we are so let's try to solve the problem. The problem is predicting the house prices. So we are given some features like number of bedrooms, bathrooms, and car parkings. So we want to predict the price of the house. So for simplicity now, we will consider only one feature like the number of bedrooms, and given the number of bedrooms, we want to predict the price of the house, right? So if I plot these two, how will I solve this problem by using linear regression, right? So if I plot this, if these are the number of bedrooms here, and here we have prices on y-axis, right? Now usually if I plot this data as the number of bedrooms increases, as the number of bedrooms increases, right, the price of the house increases, right? If I plot this data like this, as the number of bedrooms increase, the price of the house will increase, right? So that's why I got this plot. So in linear regression, what we try to do is we try to find the line which passes through maximum of these data points. We try to find the line which passes through maximum data points like this, right? You see this line is passing through maximum data points. It's not passing through this and this data point, right? But our objective is to find a line which passes through maximum of these data points. So these data points are, this is number of bedrooms, let's say this is number of bedrooms are 1, and let's say some price here, right? That's how we plotted this data. So now if we know the equation of line is y is equal to mx plus c, right? Where m is the slope and c is the intercept, y-intercept. Now similarly, I can write the equation for this line, right? So price is equal to, right? So this on x-axis I have number of bedrooms, and this slope m into number of bedrooms plus c is the y-intercept, right? So that's the equation of this line. Now if I generalize this equation, so y is equal to w1 into x plus w1 into x plus w0, right? So just to generalize this, I rewrote this equation m as w1 and this c as w0. So this w1 is the slope and w0 is the y-intercept, right? So this is the equation of the line. So our objective is, now in this equation, if you see, these x and y are fixed because they are coming from the data set. They are coming from the data set. What are the variables? The variables are only w1 and w0. So what we are actually trying to do is we are trying to find the best w1 and w0 such that the line passes through maximum data points, right? That means when the line passes through maximum data points, it's called as best fit line, right? And when we have best fit line, we have minimum errors, right? We have minimum errors. What do we mean by errors? By errors, we mean if I consider, so what this line represents? This line represents the predicted y's, right? And these crosses represent the actual y. Now, if we let's say talk about this data point, if I talk about, let's say, this data point, its predicted y is, this is the predicted y is on this line, right? So predicted y hat, let's call predicted y is y hat, and actual y is y. Actual output or actual value of y is, let's say, y. So both are same because the predicted is this line, no? The point on line represents predicted, right? If I take this data point here, somewhere here, right? So for this number of bedrooms, the predicted y, this is the price. This is the price. If I So the predicted price and the actual price are same, right? The predicted price is the line, and that is this point, and actual price is also this, right? So that means predicted and actual are same. Now, if I consider for this data point, so the predicted is this one, predicted price is this one, and this is the actual one. This is the actual price of this house, right? So there is no there is a difference between actual and predicted. So the difference between actual and predicted is called as error. Error is equal to difference between actual and predicted, y minus y hat, right? Similarly, now if you consider this point, right? If you consider this point for this po for this point here, right? So the actual is here. The actual is here, right? Sorry, this is the predicted, not actual. This is the predicted, and this is the actual, right? So there is a difference between actual and predicted, right? So again, error here is y minus y hat, right? Now the point to note is, so this error, which is for let's say this point, this error is negative. Why? Because this is predicted is greater than actual, right? So this is greater than this, so this error will be negative. Or whereas for this point, the error will be positive because this y is greater than y hat, right? For this point, error will be 0 because y and y hat are same, right? So if I write, there are two types of error which we consider normally. The first type of error, which is the simplest error measure, right? So what is that error? That is called as mean absolute error. Mean absolute error. As the error can be positive or negative, we want to take the absolute value of the error, right? And we have to minimize that. Whether negative error whether it's the positive value or negative value, we want to just take the absolute value and we want to minimize that. So that error, right? So that error can be called as mean error, absolute error, right? So absolute error can be taken by, let's say, absolute error is equal to this mod of y minus y hat, y minus y hat. This is the absolute error. And we want to take the mean of all the errors for all the data points. Let's say there are n data points. So error is equal to 1 by n, right? Because we want to take mean for all the data points, summation of I is equal to 1 to n yi minus yi hat, right? So this error is called as mean absolute error, and we want to minimize this error. Minimize this error. We want to minimize this error. This is mean because we have here n, right? 1 by n, right, for all data points. And this is absolute because we are considering only absolute value. This is one kind of error. This is also called as MAE, right? And there is another error called as mean squared error, which is equal to again mean for all data points, summation over I is equal to 1 to n yi minus yi hat whole square. Here we are taking the square. Again, the reason for taking square is we want to have the absolute value, the positive value, right? When this, it does not matter whether this is bigger or this is bigger. The value we are getting here is the positive value, right? So that's why. So this is called as mean squared error, or MSE, and this is called as mean absolute error. So these both are measures used to solve the optimization problem of linear regression, right? Okay, so we talked about linear regression for two by considering only one feature. So how can we extend this problem, right? So the problem was y is equal to w1 x plus W0, right? So this was the equation of the line, right? So this is a linear line. That's why, right? This is a linear line with only, here we are considering only one feature, right? Now, if I extend this to have multiple features, so I can say y is equal to w1x, let's say xi1. If I call this data, we have, let's say, multiple features. Uh, for ith data point, the feature 1 plus w2 xi2 plus w3 xi3, or if I consider only two features here, so how this equation looks like, plus w0, right? Here we have, for a data point I, we have two features. Those are xi1 and xi2, right? So this is first feature and second feature. So given two features, how can we predict the value? Let's say number of bedrooms, and now we are also considering number of bathrooms. This is number of bedrooms and this is number of bathrooms, right? And then this is y is nothing but the price, right? So what, again, here we are trying to find w1, this is w2, I'm sorry, this is w1 xi1 plus w2 xi2 plus w0. So we are trying to find the optimal w1, w2 and w0, which will minimize the error. Our problem ultimately becomes finding w and w0, right? Now this w can be a vector, or it is a vector if, because w has two values, no, w1 and w2. So we are finding, and this w0 is a scalar because it's a single, it's only w0, but whereas this w can be w1, w2, w3. That's why it's a vector and it's a scalar. So we are trying to find the optimal w, which will minimize argmin of error, right? So this error can be either mean squared error or simply squared error, or it can be mean absolute error. So we want to find w and w0. We want to find w and w0, which will minimize the error. That's the optimization problem of linear regression. So we will we'll use linear regression to actually predict the prices of the house, and how we can use, or how we can solve this linear regression problem by using neural networks, we'll see in the next video.